Hi, so in this video, I want to go over this exercise. It's a really long exercise, and my goal is to cover at least part A and part B, and then maybe I can make separate videos for the rest of the part. Okay, so let's read the problem together. So we have a measure space. So mu is given, but we don't know anything about mu. It could be finite, sigma finite, or infinite measure. Okay, and then we have a set E that is called locally measurable. If E intersect A is in M for all A in M, such that measure of A is finite. So it is a collection of subset of X, such that if the subset intersect any measurable set A with finite measure, it still belongs to M. So sorry, I think I didn't describe that well. So E is in X is called locally measurable if so we know E is the subset of X, right? So if E intersect A, and notice that could be any A for all A in M with mu A is finite. Okay, and I think it is intuitively makes sense to call it locally measurable, because if you have a space X, for example, and then you have E here, and E itself may be not measurable, but once you intersect with A, where A is in M, and mu of A is finite, then the intersection is measurable. So you can think like A to be like a local intuitively like local behavior of E, because it's finite, because the measure of A is finite, and then the intersection of such set is in the sigma algebra M. Okay, so that is called local measurable sets, and let M bar be the collection of all and let M bar be the collection of all locally measurable sets. So M bar is a collection of such sets E satisfy those characterizations. So let me write M bar is equal to E is a subset of X, such that E intersect A is in M for all A with measure A is finite. Okay. Okay, so clearly we have M is a subset of M delta. Why that is true? So let's give a brief proof, because let E is in M, right? Then for any A in M, finite dimension, then V intersect A. Of course, by definition of sigma algebra, this is also in M. So therefore, E is in delta. Okay. So the only thing is, if we have also delta is a subset of M, then mu is called saturated. The mu is called saturated. Okay. So let's work on part A. So if mu is sigma finite, then mu is saturated. Okay, so mu is sigma finite means so for example, we want to show that so let's state our goal first. We want to show that mu is saturated, right? So that means in particular M tilde is equal to M, but since we already have one side of inclusion, so we just need to focus on proving the other side of inclusion. So when we have M tilde, that is a subset of M. So we want to show this, right? So let me M tilde. So we want to show using right? Okay. Mu is sigma finite. So let's think about this. Implies if and only if for all E subset of X, there subset of there exists union of EJ such that E is equal to the union of EJ with the measure of EJ with EJ is in M and the measure of EJ is finite. Okay, so okay, and since we have E is in tilde, right? That implies for all A in M with mu of A is finite, we know that E intersect A is in M. Okay. Let's think about this. Eventually, we want to show that E is in M, but now we don't know if E is in M, but we know that E intersect A is in M. Well, okay, so think about this. If you have set E and you know A is here, right? And then the rest is AC. So those part, so those part are AC. And of course, E is equal to E intersect A union E intersect AC, right? And then we know already this is in M. So AC could be, well, if AC is finite, then we're done because because AC is in M and AC is finite, so E intersect AC is definitely in M. But here we want to consider the case in general, right? So AC could be like mu of AC is equal to infinity, but okay, but since mu is sigma finite, we know that but since mu is sigma finite, we know that mu is sigma finite. We know that there exists E J 1 to infinity such that EJs are in M and mu of EJ is finite. Okay, then what do we have now? Sorry about that. And AC is equal to the union of EJ where J equals to 1 to infinity. Hence, E intersect AC is equal to E intersect the union from 1 to infinity of EJ, which is equal to union of the E intersect. Now I realize my notation choice is not very wise, so let me call this AJ, AJ, and let me call this AJ, and let me call this AJ. J, AJ. Okay, so we have E intersect AJ and from 1 to infinity. And then what do we have? And then what do we have is we have E intersect AC is equal to Z. So of course, because the measure of AJ are finite and AJ is in M, so therefore this is in M, given that E is M tilde, in M tilde. And then the union of sets in M is still in M. Therefore, E intersect AC is in M. So therefore, so if we write all the way here, so this is in M, and we're done with part 1, right? Because we show that E is in M, and that's what we want to do because we have E is in M tilde, and now we want to show E is in M, and we're done. Okay, and let's work on number 2. So number 1 is okay, and I think number 2 is also okay, but for some reason, for obvious reason that Fola want us to get more better understanding on this. So the rest of the problem, it took me a really long time. Okay, anyway, so for part B, so we want to show that M tilde is a sigma algebra, right? And then look at the definitions. So M tilde is a sigma algebra. The first thing we want to show is that we want to specify, we want to make sure is a sigma algebra on which universal set. So here we give 1 second or 2 seconds thought. So this is a sigma algebra on X. So this is like the thing that is too obvious. So the author didn't give us the second half of the second part of this sentence, but you should be always keep in mind, because when you try to prove it is sigma algebra, you need to show the definition, and then the first definition is the universal set in this set, in this collection of sets. So X is in M tilde since X, and then we call definition for M tilde, right? So X intersect A is equal to A, and A is in M, and we're done. And then for the second one is empty set. So empty set is also in M tilde since empty set intersect A is equal to empty set, which is equal to M. And then the third one is if E is in M tilde, then EC is in M tilde, right? So proof. So if I want to show EC in M tilde, we want to show that EC intersect A is in M for any A is in for any A is in M with the measure of A is finite. Okay, how to show this? Let's just write down what we have. So E is in M tilde implies E intersect A is in M for all A in the measure of A is less than finite. And then we want to show that EC intersect A is also in M. Okay, so observe that A is equal to A intersect E union A intersect E C, right? And we already know that A is in M, and we already know this is in M given the assumption that E is in M tilde. Therefore, that implies since is a sigma algebra, A intersect EC is equal to A side minus A intersect E, which is equal to A intersect EC, where EC is definitely in M, and the intersection is in M. Therefore, A intersect EC is in M, and we're done. And then for the first one is, so let E1, E2 in M delta. Then we want to show that the union of EJs is in delta, right? And then let's write down this goal explicitly using the definition of delta. So that is saying this intersect A is still in M for all A in M, and the measure of A is finite. Okay. We have this, let me see. And you can write this in a different way in the union 1 to infinity, EJ intersect A. Okay. EJ intersect A. So we have this, and then we want to show this is in M, right? Okay. This should be obvious because EJ intersect A is in M. So collect disjoint or just union of sets in M is still in M. Therefore this, and then we're done. So A and B are okay. So let's do part C together. So C is this, right? So define mu tilde on M tilde by mu tilde of E is equal to mu of E if E is in M. So this is one way to, so we're actually constructing a measure right now, right? So, and it is equal to what? Infinity, right? Otherwise, okay. Okay, the mu tilde is saturated measure on M tilde called saturation. So we know, we want to show that mu tilde, we want to show that mu tilde is, so mu tilde here we are constructing the subject object is something defined on M tilde. Right? So we want to show it is saturated measure on M tilde. So notice that the definition for saturated measure is above here, right? So if I have original M, if I have a measure on M, then M is saturated measure on M, if and only if M tilde is equal to M. And here, what we have is that M tilde is itself is a measure on M. Mu tilde is a measure defined on M tilde. So therefore, to show this, it is equivalent as showing that M double tilde is equal to M tilde. And again, the inclusion of this is trivial. Why? Let's think about this. So if E is in M tilde, that means E, okay, we already proved that M tilde is sigma algebra. So if E is in M tilde, then it follows that it satisfies those definitions, and we want to show that E is in M tilde tilde M double tilde. If E is in M double tilde, then that means if E is in M double tilde, if E is in M double tilde, that means for any, so let's just, okay, let me erase this and let me just try to show. So take E in tilde, and then we want to show E is in tilde tilde, right? And then what do we have is that means we want to write this explicitly that the E intersect A is in tilde for all A in tilde, and then the M tilde measure of A is finite. Okay, since E is in tilde and M tilde is a sigma algebra, so A intersect E is in M tilde, and in particular, if M tilde A is finite, then A intersect E is in M tilde. Okay, and then we're done. And then now we're saying that M double tilde is a subset of M tilde. Okay. Let's so take E intersect M double tilde. We want to show that E is in M tilde. Okay, and how to show that? So E intersect A is in E intersect A is in M. So for all A is in tilde, and mu tilde of A is finite. So we want to show this, right? Okay. Okay, we want to show this. Okay. Let's just write. So E is in double tilde implies what? E is in M double tilde implies E intersect, let's change the number, S is in M tilde for all S in M tilde with a measure M tilde of S is finite. And we want to show that given A, I'm sorry, so A here should be, this should be, so after I wrote down, after writing down here, so I'm looking at this. So I'm gonna, but right now, honestly, I don't have any clue how to solve this problem. So by this information, I know that S intersect A is in for all A in M, the measure of A is finite. Okay, so because this is our goal, right? So we want to show pick A in M with the measure of A is finite. So we want to show that E intersect A. So all of those statements are equivalent. So this is in M, right? So I want to show this. So okay, so we already know this is in E intersect A. S intersect A is in And what about E intersect A? E and S. Oh, and then E intersect S is in delta implies E intersect S. Intersect A is in so what we have is we know E intersect X intersect A is in and then we know that E intersect A is we're wondering about this, and we know S intersect A is in then we should be in good shape, right? So those are my draft. Let me just save it and then delete it later. So notice for all S in delta, mu S is finite, E intersect S using delta implies E intersect S intersect A because A is a finite measure in and it is it's an element in the sigma algebra. This is in M. Okay. Also, S intersect A is in and then E intersect A. Let me draw a picture, see if that's more clear. So E intersect A intersect S. So we already know that E intersect S intersect A is in M, and we also know that S intersect A is in M. So S intersect A is in M. Now I am wondering if E intersect A is in M. Okay, so we know that since S is in delta and delta is a sigma algebra, so S complement is in delta. So as complement intersect A is also in M. And now if you observe this, right? So this region is as complement intersect A. As complement intersect A, intersect E. Okay. Right. Let me make further observation. And E intersect as C. This should be in delta, right? In delta, also it implies E intersect as C intersect A, right? Is in and therefore now you look at this. Let me erase this. Is that so? The black thing here is S intersect A intersect E. So altogether, this implies that E intersect A is equal to E intersect A intersect S union E intersect A intersect SC. And then because this is in M and this is in M, so the union of two sets in M is definitely in M. Therefore, we're done because we show that E intersect A is in M. Therefore, E is in M, and we're done. And then for number 4, part D. So D, D is if mu is complete then mu bar is complete. So how do we show that? So mu is complete means it is domain includes all subsets of new sets in M, and we want to show this is complete, right? So and by definition, so its domain includes all subset of new set in M tilde. So like you can think about this as an algorithm how to solve this problem. So it's like a recipe. So the first one is pick arbitrary new set in tilde, and let's see, so pick E in tilde such that mu tilde E is equal to 0, okay? And the second one is pick arbitrary subset of E, call it E, okay? And then the third one is show that B is a subset, show that B is an element of M tilde, and 4 is show mu tilde of B is equal to 0. And this is like typical recipe for showing something is complete. And then now let's prove 3, right? So we want to show that B is an element of M tilde, okay? That is saying for any A in M with measure A is finite, then B intersect A is going to be in M. So we want to show this, okay? And we also know, what do we also know? We know that E is in M tilde. So for all A in M, mu of A is finite. E intersect A is in M. And we also know that mu tilde of E is equal to 0. And what do we know about mu tilde is equal to 0? That implies, because the way we define mu tilde, right, it is equal to mu E if E if it is equal to, if it's not measurable, then it is infinity. So because it is 0, that means mu tilde E is equal to less than infinity. Mu tilde E is equal to mu of E, and we know that the mu of E is equal to 0. And also we're given that assumption, so by assumption. So when you're doing this problem, you need to keep in mind what you have in your hand. So you can like imagine you have a invisible pocket, and you need to be flexible to know which tool to use while proving this. So by assumption, mu is complete, right? So that is one of the assumption. So because mu is complete, that means, and right, so this actually implies another thing, which is E is in M. So, and so since since E is unmeasurable, right? Since E is unmeasurable, and mu is complete, and mu of E is equal to 0 for any f in E, mu of f is equal to 0. And so I should say that before using this notation. So f is in M, and this is equal to 0. I should be able to do this. And then so that implies, so in particular, recall the B that was selected by arbitrary randomly. Okay, so in particular, B is in M, and the B and the mu B is equal to 0. And this implies that mu delta. Okay, so far we don't know yet. We don't know B is in, we're not sure, we're not quite there yet. We want to show B is in M delta, right? Yes, we want to show that B is in M delta. So since B is in M, B is in M delta. Since M is in M delta. I think also for D, mu M is equal to M delta. So we're not given anything about like a saturated measure. Or let me think. So from C here, it's actually asked us to show with mu defined on so with this we have is equal to M. But for D, we don't know if M is equal to M tilde because we're not given the condition that we're not given the condition that mu is saturated. So so this is good because here we didn't use the we didn't use the equality. We're using one conclusion, which is true all the time. Okay. Therefore, and mu tilde B is equal to, because this is equal to 0, that means mu tilde B is equal to mu B because it's because B is measurable. So mu tilde B is equal to mu B, and because mu B is equal to 0, which is 0. So together, so it's kind of like I proved 4 here. So together, B is in delta, and the mu delta of B is equal to 0, and therefore we proved D. So let me pause my video and I'll be back. Okay, let's read about number 4D. Oh, we proved D. Let's do E. Okay. I'm not sure if I can finish this, but at least I want to get in touch with number E. Okay, so let's do E. So suppose that mu is semi-finite. So semi-finite. And then you need to remember what is the definition for semi-finite. And you need to recall something we proved in, or I proved in exercise 14. So mu is semi-finite. This means for all C larger than 0, there exists a subset F. So for any E in M with the measure of E is equal to infinity, for all C is larger than 0, there exists, for all C larger than 0, there exists an F. There exists F. There exists F. There exists F. a subset of E such that for all C larger than 0, there exists F in E such that the measure of F is not too small and it is finite. So we prove this in exercise 1.14 Poland. And then for E is in delta, we define a new measure. So basically the purpose of E is, so in part C, we showed and we proved the existence of a measure mu delta satisfy, like it constructed in that way, and then it is a measure and it is saturated measure on M delta. And part E is like we construct, or the author let us to construct something and we prove it is a measure, and it is also a saturated measure on M delta. So the purpose of this problem is to introduce you the definition for saturated measure and then tell you that, okay, saturated measure is actually not unique. There are two ways, and there may be more ways to construct a saturated measure. And one, so the first one is in part C, and the second one is in part E, and then you show both are saturated measures that have certain properties and they're different. And for part F, if you look at that, it's actually showing that those two measures are not the same. So saturated measure on M delta is not unique. Okay, so continue part E. So for E is in M. So suppose mu is semi-finite, and we have this. So for E is in M delta, we define mu bar of E is equal to supremum of mu of E, where A is in M and A is a subset of E. Measure mu, okay, and then we want to show, so we want to show mu bar is saturated measure on delta that extends. So when you look at a statement, there are more than one task to do. So here, let's just separate them out. So define, well, because the input of mu bar is really just one set in M delta, we don't need to show it is well-defined because it is well-defined. But if your, for example, if E can be expressed in the union of two sets where those two unions is not unique, so E could be equal to F1 union F2, or it could be the union of F3 is equal to F4. Then in that case, you have to show well-definedness. But here is okay because the input just E. So define mu bar is not defined, but check. So check mu bar is check mu bar is a measure. Okay. We want to check mu bar is a measure. And the second thing is mu bar is saturated measure on delta. Okay, that extends mu. Saturated measure on delta that extends mu. Okay, and third one is M bar extends mu. So those are the three that we need to prove. I will include this in the next video, and I'll stop here.